Hi friends, I am Dr.R.MaliniDevi, Associate Professor of Mathematics, PG Research Department of Mathematics. The standard for was Rajaratnam College for Women, Sivagasi. Now we are discuss about the topic uncountable sets. First see the learning objectives of this video. The learning objective is to know about the uncountable set, first point. Next one, uncountable sets are the fundamental concepts in mathematics, especially in real analysis. Next objective is they represent a set whose elements cannot be put into an one-to-one correspondence with the natural number n. Next one is, first we see the countable set, then only you have to see the uncountable set. A set is called dunerable or countably infinite set if there exists an 1-1 mapping from a set n of a natural number onto a set S is a countable set. A set A is said to be countable if it is either a dunerable or A is finite. Dunerable means countably infinite set. A countable set is called a finite or infinite set. A set A is said to be countable if it is finite or countably infinite set. Countably infinite means the dunerable set or enumerable sets. Now see that example, the set of all whole numbers W, the W starts from 0, 1 to etc. Countable set means there is one-to-one correspondence mapping from a natural number onto a set A is countable. Here the whole number is one-to-one correspondence between the natural number n, who n starts from 1, 2, 3 etc. Therefore, one-to-one correspondence between the whole number and also a natural number. Therefore, the set W is a countable set. Next one is set of all integers. Set of all integers is also a countable set. So, here there exists a one-to-one correspondence between the natural number, that is bijection between their natural numbers. So, the Z is also a countable set. Next one is set of all prime numbers. Here the prime numbers exist a one-to-one correspondence between their natural numbers. Therefore, the prime number is also a countable set. The whole number, integers and prime numbers are all a countable set. Next we see that uncountable set. A set is considered uncountable. Uncountable means it is impossible to enumerate its element using natural number. That is, there is no one correspondence between the natural numbers is called an uncountable set. In other words, we say that a set A is countable if there exists between a one-to-one correspondence between the natural numbers. A set A is not countable, it is called an uncountable. In other words, a set A is called uncountable if A is finite, infinite and A is not cardinality equivalent to that n. That is, there is no one-to-one correspondence between that natural number n is called an uncountable set. Uncountable means non-dunerable sets and also not non-enumerable sets. Now see, next we see that the theorem for uncountable set. We say that the open interval 0, close interval 1 is uncountable. First we take the open interval 0, 1 can be uniquely as non-terminating decimals, that we like that 0.A1, A2, A3 etc. An. Here the elements A1, A2, A3 etc. An lies between 0 less than or equal to AI or the value is less than or equal to 9 for each I. Subject to the following restriction that any terminating decimals we can write as point A1, A2, A3 etc. An etc. 0 etc. This can be written as the last number is 0, 0, 0. This number can be written as An minus 1. Point A1, A2, A3 etc. An minus 1 into 999. For example, we say that 0.54. The 0.54 can be written as the round of the value is 0.5399. The third decimal value is 9. 9 is round of 2. 53 can round of 54. Next one is 1. 1 can be written in the decimal value is 0.999. So, the round of a 0.99 is 1. Suppose we taken that the set open interval 0, close interval 1 is a countable set. We know that countable set is one-to-one correspondence between that natural numbers. So then the element open interval 0, close interval 1 can be listed as the element x1, x2, etc., xn, etc. Where x1 can be written in the form of a11, a12, etc., a1n. Similarly, x2 can be written in the form of a21, a22, etc., a2n. Up to the element of xn, xan1, an2, etc., ann, etc. Now, for each positive integer n, choose an integer bn. We have to choose an integer bn such that the bn is also lies between the element 0 and 9, less than or equal to 9. So, bn value is equivalent to 0 or equivalent to bn or value is not equal to 0 and bn value is not equal to ann terms. Now, you have to take choose a positive integer n, choose a positive integer n and choose a positive integer bn in that form of 0 less than or equal to bn, bn less than or equal to a. Here the condition is bn is not equal to 0 and bn or value is not equal to ann. Now, write the element for now construct the value for b1, b2, etc. up to the term the value is bn. So, we write that point, we have to construct y is equal to point b1, point b2, etc., point b3. This is a decimal value. Here the y value is lies between open interval 0, 1. Also, y is different from each I at least in that ith places. Suppose we taken the second place or third place, so x3, third place means x3, y is different from for each xi at least in that ith places. Hence, y is not equal to xi for each I, which is a contradiction for our hypothesis. Now, assume that the set A is countable set. We get that a contradiction, hence we get open interval 0, close interval 1 is also a uncountable set. Next, we see that example corollary for a uncountable set. A subset A of R which contains open interval 0, close interval 1 is uncountable. Suppose we take that a set A is countable set. A subset open interval 0, close interval 1 is also a subset of R. To prove that open interval 0, close interval 1 is a uncountable set, suppose A is we have taken that, assume that is countable set. We already know that any subset of a countable set is countable. Therefore, A is also a subset of R, so A is countable. But here A is open interval 0, 1 countable. By the subset is open interval 1 is uncountable set, which is a contradiction. Therefore, A is uncountable. Assume that A is countable, we get that result is open interval 0, 1 is countable. Suppose A is not countable, A is uncountable, therefore we get open interval 0, 1 is uncountable set. Next, see the example for countable set. R is uncountable. Here there is no bijection, one-to-one correspondence between the real number and also a set of a natural number. So, R is uncountable. In our definition, not a countable set is called an uncountable set. Not a countable set means there is no one-to-one correspondence between that natural numbers R. Here there is no bijective functions between a set R and a set of all natural number. Therefore, the real number R is uncountable. Next, we see the next example for set of all irrational number is countable. Suppose we taken that the set of all irrational number is countable. We know that the set of all rational number is countable. So, the countable S union Q. S is irrational number, Q is rational number, union of S union Q is equal to, we get the whole number, that is R. This is also countable. Countable union of countable set is countable. Therefore, we get R is countable, which is a contradiction. Therefore, our assumption is wrong. Therefore, we get that S is uncountable set. Next, we see that properties are uncountable set. Uncountable set possess unique property that distinguish them from countable set. These properties are crucial for understanding their role in real analysis. Now going to the no limit for an subsets. Uncountable sets have an infinite number of subsets and these subsets can be uncountable themselves. Next we see that proper set property. The proper set of any uncountable set is also an uncountable set. These are the properties of uncountable sets. Next, comparing between the countable set and also an uncountable set. First we see that cardinality property between the countable set and uncountable set. Cardinality means number of element in that set. So, in a countable set can be put in one-to-one correspondence with that natural numbers we get that in that countable set. Cannot be an one-to-one correspondence between the natural number is an uncountable set. Some more example for countable set and also an uncountable set. In an example for countable sets are set of all integers, rational numbers and even numbers. These are example for countable set. Some of the example for uncountable set is set of all real numbers, irrational numbers. We see that the functions is also uncountable set, continuous functions. These are the example for uncountable set. Next we see that subset property of countable set and also a uncountable set. Can have a finite or countable number of subsets in a countable set. Can have an uncountable set can have an infinite number of subsets which can be an uncountable set. These are the comparisons between countable set and uncountable set by using cardinality property and also in subset property. Next we see the application of uncountable set. Some of the applications in real life situations in probability theory, physics and computer science. First see that probability theory. Uncountable sets plays a vital role in probability theory, particularly in that function is continuous probability distribution functions. Next one is physics. In physics, uncountable sets are used in model involving continuous quantities like wave functions in quantum mechanics. Next we go into computer science. In the field of computer science, uncountable sets are employed in the areas like computational geometry, data analysis to represent the continuous data. So, now the overview of our countable set is, first we see that countable set, next one is example for countable set. What is meant by countable set? Next one is what are the example for countable set? Next is what is meant by uncountable set? Next we see that the open interval 0, 1 is uncountable set. By using theorem you prove that one corollary, one result, a subset of a countable set is countable. Here any subset of R which is an uncountable set. Some of the examples of uncountable set. Next we see that properties of uncountable sets and comparing between the countable set and uncountable sets. The last one is applications of uncountable set. I hope you are like this video. Thank you for watching this video. Thank you very much.